Okay, in this video we're going to begin our discussion of welding. Chapter 9 is primarily welding, although it does talk a little bit about bonding or gluing operations. And so we'll start off in this chapter, first of all, by looking at weld symbols. We see a sample weld symbol which shows all the various kind of things that could go onto a weld symbol that would be placed on a drawing. And what we're going to do is look at much simpler ones and learn this more by example than anything else. But you will notice that a weld symbol generally includes an arrow, a kink, and a straight line. And later on we're going to be talking about the arrow side and the other side. You can see make notes here of arrow side and other side. Scroll on down. And so we would see a welding symbol. We'll actually take this weld symbol and move the arrow so that it's right there. And this says we're going to place what's called a fillet weld, or a triangular shaped weld. It has a 5mm leg size, the length of this segment or the length of this segment. And we're going to place that fillet weld on the arrow side. And if the arrow is pointing to here, we're also going to place it on the other side. So this would be the other side. A similar symbol, this again says triangular fillet welds. These fillet welds are going to have a length of 60mm with a center to center spacing of 200mm. And we're going to do that on the arrow side, and we're going to do that on the other side. We probably also, in this one, should have an indication of the leg size. A circle in the kink generally means all the way around. And so this would be a circular pipe welded to a plate. The all the way around symbol says, the symbol together says, let's have a fillet weld, 5mm leg size, all the way around. This would say a parallel cutting of the two plates, leaving a gap. And then let's do a butt weld on both sides. This says cut a V on one side, leaving a 2mm gap in the V. And then we'll weld on the one side. This says cut V's, or in fact, so cut a V on the weld side, cut a V on the other side. This says cut a bevel, or a 45-degree notch, on one side. This would say cut a 45-degree bevel and fill it with a fillet weld, and do the same thing on both sides. This would be a one-sided U-shaped notch. A one side on one plate only U-shaped notch. This would be a simple fillet weld between these two plates, and this would be a parallel weld or a butt weld between these two plates. You'll see a few more weld symbols, and we'll talk about that just a bit more, but not much more. Okay, now getting into the stresses calculated in both butt and fillet welds. We'll deal with the butt weld first. Okay, first of all, you can see that we have two plates of the same thickness. Those plates have been welded together. There is some excess material beyond the thickness of the plates called reinforcement. We generally ignore that material. We're going to load this butt joint in tension, or we're going to load this butt joint in direct shear. It doesn't matter because we're going to calculate the stress the same way, and stress is going to be the force divided by the area of the throat. Notice the throat area labeled H. Notice it only includes the thickness of the parent materials. It does not include the thickness of any reinforcements. So the area would be the height here times the length. So sigma is equal to F over HL. Very easy computation. Okay, whether it's a sigma in this one or a tau, a shear stress, in this one. That takes care of butt welds. Now look at fillet welds. And to make this thing balance out nicely and not introduce any bending into this system, we're going to have a center plate, and to that center plate we'll have two outer plates welded with the fillet weld to the center plate, applying 2F to this side and applying F to each of these locations. So our forces balance, but we don't introduce a bending moment into any of the plates. And now what we want to talk about is, for this kind of loading of a fillet weld, what kind of stresses do we see in the weld material itself, realizing that there is no connection between the plates here. They're touching, but they're not connected together. So what we can do is realize that within this material we might cut different planes and then look at it statically. So if we make a cut through this weld material at an angle theta, and we keep this upper half, then we can do a force balance that says there's going to be a tensile force acting normal to this surface, and there's going to be a shear force acting on this surface, and statically the sum of the forces in the x direction here have to equal this x force, and the sum of the forces in the y direction here have to equal 0, and those can be put together and computed, and we can come up with the value of the shear stress in this weld, in this section, and the normal stress. Those would be right here, and those can be written as a function of the angle theta right back up here, which is the angle that we decide to investigate. Now, we can then take these two stresses and combine them either in a Mohr circle way. In this case, we're going to combine them in a von Mises way, and we can come up with the von Mises stress at that angle in the surface. An interesting question says, we can pick any theta we want, but is there a theta which produces a maximum combined normal and shear stress combined in a von Mises way? And there is a value of the angle theta that does that. It turns out that the value of that angle theta is 62.5 degrees, which then gives us our shear stresses and normal stresses. It turns out that when you compare this with experimental work, that this compares very, very badly. This whole argument seems mathematically very reasonable, but it just doesn't compare well with experiments. And so that's my reason for the note right here that says, wow, no analytical approach that predicts the stresses well, because they don't match experimental. Well, there is no analytical approach that matches the stresses well. So what are we going to do? Okay, and so I say this is a very important paragraph in your textbook, so let's read it. It says, still in the absence of robust analysis, weldments must be specified and the resulting joints must be safe. So what that says is we're going to use welds, and we have to design them and specify their sizes so that they are safe. Okay, so the approach that's generally used is a simple approach that is conservative, that has been verified to be conservative by testing. And the approach is consider the external loading to be carried by shear forces only. Okay, so from now on, when we see fillet welds, we're going to be calculating shear stresses. Shear stresses in the throat area of the weld. We're going to ignore the normal stress and only look at shear. Okay, and we'll use distortion energy for any significant stresses. Okay, and this is supported by the code. And so if we were to look, let's see, if we were to look at what that says, first of all, we need to define throat. Let's see, where is that? Okay, right here. See the label throat? Okay, throat is this thickness measured on a 45-degree line. Okay, and so if this leg size is h, then this throat distance is 0.707 times h, which is sine or cosine of 45 degrees. That'll be our throat size, and we'll need to calculate, when we're doing stress calculations, the area through the throat of all of the welds. Okay, and so let's take a look at what we have to do to calculate stresses in welded joints. And this says loaded in torsion. I guess we'll accept that notation, except it's more than torsion, it's also a direct shear. And this picture, you need to look at it and see that it's very much like the bolts and shear situation that we saw at the end of the last chapter, that we have a wall of some kind. To that wall we're going to weld a plate. Both of them are almost in the same plane, but rather than drilling holes into material and putting bolts through there to represent the direct force and the moment created by this direct force, and calculating primary and secondary shear stresses for bolts, we're instead going to do the same thing for welds. Okay, and so at any point in these welds, we will have a primary shear force which will be the weld shear of this load. But then we'll also have secondary shear forces that end up being perpendicular to radius vectors that have to be combined as vectors. So this picture probably looks, hopefully by now, looks fairly familiar to you. One of the things we're going to have to do, as we did with bolts, is we're going to have to find the centroid of the bolt group. Then we'll have to find some significant properties of the bolt group. Let's see, finding the centroid of the bolt group can be done in a composite way. Let's just talk about what's happening in this picture. This is two different weld lines. Each weld line is of a different thickness. The thickness of each weld line is 0.707 times its H, but they have different H sizes. So first thing we would do is we would find the centroid of this weld group, which means find the centroid of this one, find the centroid of this one all by itself, combine them properly, and the way we're going to combine the centroids is that x bar is summation AX over summation A. Y bar is summation AY over summation A. So one of the things we need is this summation A, which is the sum of the two areas of the welds, which is A1 plus A2, which is B times D1 plus B2 times D2, where D2 is the 0.707H, okay, and B2 is the length of that weld segment. So calculating this, calculating each of these, this would give us the centroid of the weld group. Now what we're going to also want, because we're going to be doing, interestingly enough, in this shear loading, we're going to be doing a force over area calculation, but we're also going to be doing a TR over J calculation. And so we're going to need to calculate the J value, okay, and that can be done in an incremental process. Each rectangular weld segment has a moment of inertia about a particular axis, and since they're rectangles, that can be computed as a BH cubed over 12. We just have to be careful which one we're cubing. And so if we want to calculate moment of inertia about the x, for this one will be its b times d cubed over 12. For this one, its moment of inertia about the x will be this one called b and this one called d. That's a little different, where b in this case is 0.707H, so db cubed over 12. But that for each one gives the moment of inertia about their own centroid. Now we have to use parallel axis theorem to come up with moments of inertia about the actual centroid of the system. Okay, and what we're going to do is, and we have IX, we have IX and IY for weld 1. I didn't say that right. We have an IX for this weld. We have an IY for this weld, okay, about its own centroid. And so we can calculate a J value for this one about its own centroid just by adding them together. We do the same thing for this other weld, calculate its moment of inertia, sort of like a BH cubed over 12 and an HB cubed over 12. Calculate both of them, add them together. That gives us a J value about their own centroid. Now we need to calculate the distance we're going to move this one's moment of inertia from its own centroid to the centroid of the system, and we need to calculate the distance we're going to move this one's moment of inertia from its own centroid to the centroid of the system. And so those radiuses can be calculated from the geometry that's given, knowing where the centroid is located. And then our final J value is going to be the J about the local centroid plus an AR squared, and for the other rectangle, J2 plus AR squared. It's a combined process that can be done for any shape if you just do it carefully. What's nice is the author gives us J values, these J values, polar moments of inertia, for lots of different shapes, including a single straight line, two parallel lines, two welds of different length forming a right angle, welds forming a C, welds forming a rectangle, and welds forming a circle. And in this table, they'll give us the total area of the weld segment. They'll give us equations for the location of the CG of the weld group. Then they give us what's called a unit second polar moment of area. Okay, unit means this number needs to be multiplied by the weld throat dimension. So this does assume in this one that all welds have the same throat size, okay, and have the same leg size. And so if I want to know the moment of inertia of this shape, I calculate the unit moment of inertia, and then I multiply by the throat thickness, which is 0.707 times h. Let's see where they make note of that. Yes, the actual J value of any weld shape is 0.707 h times the Ju, which comes out of this table. Okay, so if we can find our shape in the table, great, we don't have to do the work that was presented above. What we have in example 9.1 is a weld, which would be a vertical weld line here, a vertical weld line here, and then this would indicate horizontal welds along here, and we have two verticals here and a horizontal one, two verticals on this side and a horizontal one. The problem is symmetric because of the loading, and so we're going to actually just analyze only half of the problem. So what we have is, if we look at the weld shape, is a vertical line, a horizontal line, and a vertical line. And we're going to need to then calculate the area of the weld. We're going to need to calculate the moment of inertia of the weld. Excuse me. Okay, I paused for a second, but I'm back. And what we have is, again, this shape. We need to calculate its area, we need to calculate its centroid, and we need to calculate its polar moment of inertia. Now notice the loading up here that is offset in the horizontal direction. That loading can be replaced by a direct shear of the same size and the moment that it produces. The direct shear will create primary shear stresses in the weld, the same everywhere, same direction. It's just going to be a force over area. But this moment is going to create secondary shear stresses that at every key point within the weld will look very much like the bolt secondary shear stresses. So here's our shape. This is a picture that shows at every corner, which is generally where the high stresses are, at every corner we see precisely the same primary shear. That, and that, all horizontal, all of the same size. But then we see different secondary shears, where here's the secondary shear perpendicular to that radius line, secondary shear here perpendicular to that radius line, secondary shear here perpendicular to the radius line, secondary shear here perpendicular, and then it shows the vector combination of this secondary shear and that primary shear. Secondary shear combined with primary shear, secondary shear combined with primary shear, etc. Okay, again, if we look at it carefully, we can probably figure out where the worst case would be. And the worst case is probably going to be right. Let's see, both of these. Yeah, both of these combined about the same. And on the bottom, they subtract in both directions. So either one of these two corners ought to have the same effect. Okay, so let's look now at more of the details. First of all, we know the total length of all these weld segments, so we can get the area as 0.707 times the leg size. That's the throat size. Then we have two 56 millimeter vertical segments and a 190 millimeter horizontal segment. So area of the throat times total length of the weld. Okay, primary shear stress is V over A. So we have 25,000 pounds of load divided by a 1280 millimeter. Let's see, no, that's not 25. This is 25 newtons divided by 1280 square millimeters to give us kilopascals. Let's check that load. Make sure. Let's find it. No, it was a kilonewton load. That's right. 25 kilonewton load. Primary shear of 19.5 megapascals everywhere. Now, calculating the centroid of the weld, the X bar, and let's see what directions we have labeled here. Okay, that's got a Y on it. And okay, so apparently this is called X. First of all, the centroid this way is easy. It's right in the middle. Okay, the centroid in this vertical direction would be the area of this times half its height would be where centroid is located, as measured probably from the very bottom. Okay, then the area of this times its distance from whatever our reference dimension would be. Let's look at exactly how they put the equation together, and then we'll be able to tell what their reference was. Okay, 56 squared over 2 times 56 plus 190. Sorry, I know what they're doing. They're not, that formula does not jump into my mind right away. What they're doing is they went back here and they found the shape. Okay, and so here is the formula. Okay, we could have derived it algebraically. I just wasn't seeing it. But so here's the formula for this C shape for the X bar and the Y bar. Again, the Y bar was the easy one to find. It's right in the middle. We're going to be doing this JU in a little while for this shape, so we'll be coming back to that. Okay, so we have X bar coming from the table. For these welds, we're going to need to calculate these R distances. Okay, but rather than using what we did with the bolts, which was an MR over summation R squared, we're going to use a TR over J calculation. So we do need J. And here's J that's calculated using the formula from the table that we passed through earlier. Okay, now our moment, or torque if you want to call it that, is the force that's been transferred to the centroid times the distance to the centroid perpendicular to the force. And so that was a 25 kilonewton force times a distance of 100 to the top of the weld plus an additional 10.4 to get to the centroid of the weld. Okay, and so our secondary shear stress is a TR over J or an MR over J, if we're going to call it M here. Okay, and A and B have the same radius of 105. C and D have the same radius of 95.6, and therefore they calculate out to have slightly different secondary shear stresses. I believe, let's see, I think, was it C and D on top? They were closer, A and B on the bottom. Let's go find out. Yes, A and B on the bottom have longer radiuses. C and D on top have shorter radiuses. So we've done TR over J calculations at all 4 key points. And now all we have to do is a vector combination of the stresses. The author doesn't offer any assistance on that other than just do it. The vector flip-flop method that we used with bolts will work just fine here. You use whatever method you like. Okay, and from that we can calculate the shear stress in the weld. Okay, stresses in welded joints in bending, different kind of loading. Okay, here's a weld here on the top side. We have a weld on the bottom side. So if we look at it, we have 2 parallel segments of weld. We're going to apply a load out here. That load is going to apply to create a direct shear, which will be force over area, but it's also going to create stresses in these corners that would come from what we would call traditional bending, an MC over I calculation, which means we're going to need the moment of inertia of this weld pattern, okay, not the polar moment of inertia, okay. We're going to need the area moments of inertia about an appropriate axis, and for this loading it would be about a horizontal axis, about a z-axis, which will be the larger moment of inertia. We don't want the smaller moment of inertia, which would be about that y-axis. And so just as we saw with polar moments of inertia, we're also going to find tables of weld shapes, and we're going to have unit values of our area moments of inertia. We'll see that in just a moment. This one, let's see. Yes, it is going to use the table. We could have figured this one out ourselves, but let's go look at the table. This one shows two vertical weld lines, and this entire table, which is unit second moment of area, assumes that we're always going to be loading and bending about a horizontal axis, and that's the moment of inertia that it gives us, a moment of inertia about a horizontal axis through the centroid. So in this case, if we're going to have a horizontal axis, these are the welds that we have, these two horizontal lines, not these two vertical lines. Okay, and as we would expect, it says that the X bar, Y bar is at the center, and the area is going to be 1.14 HD. Why is that? D. Actually, I'm somewhat skeptical of that. It ought to be the length of this line times throat area plus the length of that line, but they're the same, so it should be multiplying by 2. And 2 times 0.707 is a 1.414. I think this probably should be 1.414 HB, not D. This one area should be 1.414 HD. I believe they've blown it there. Moment of inertia about the horizontal axis, BD squared over 2. They referred to that. These are also, but these are unit second moments of inertia, so we have to multiply by the thickness through the throat, 0.707 H. Going back, the moment of inertia, unit moment of inertia, BD squared over 2, and then the total moment of inertia is 0.707 H times that unit moment of inertia. Getting past that, okay, and so they didn't really finish this one up. Now the calculations that we're going to do for this weld will be a direct shear of V over A and a set of stresses coming out of moving left right in this picture. Tension in the top, compression in the bottom, which will come from an MC over I. C will be the distance from the neutral axis to the outer fiber. Here's the I value that we're going to use. And M will be this force times the length of this beam. That would be the bending moment for this problem. Okay, so that would take care of weld stresses. Finally, we need to talk about a couple of things. The strength of the weld, so that we can compare it to stresses, and then any design requirements that we would have. Okay, and so here is the strength of various weld electrodes, okay, or welding wire, and it gives minimum properties that we can design to. Sounds very much like proof properties, okay, and various electrode numbers. Says an E60 family of welding electrodes. Those have tensile strengths of 62 kpsi, or 427 megapascals. They have yield strengths lower, so this is more like an ultimate tensile. Yield strengths of 50. Okay, give us percent elongation numbers to give us an idea related to the ductility. So we can choose different wires or welding electrodes that would have different strengths that would be appropriate for the job. Now, need to think about what kind of allowable stresses we can put into welds, and then that would also build in a factor of safety. If we have a butt weld in tension, it's one of the first things that we saw there. The welding code allows us to take that weld stress up to 60% of the yield stress of the weld material. Doing that builds in a factor of safety of 1.67. If we have butt welds in bearing, because that is in compression, we can take that up to 90% of the yield strength. If we have butt welds in bending, we can take that again up to 60 to 60% of yield strength, and we're talking only about butt welds. If we have simple compression of a butt weld, again 60% of yielding. Now, here's the one that we're going to have most often. If we're talking about fillet welds, okay, or butt welds, or most of the time we're going to be dealing with fillet welds. Fillet welds loaded in pure shear, we're going to use 30% of the ultimate tensile strength. That's what the code allows, 30% of the ultimate tensile strength, not the yield. Okay, this basically comes from yield being a certain fraction of ultimate tensile, followed by a von Mises kind of assumption, roughly, that shear is roughly 0.577 times the yield. So here are our strength requirements. There's a very important note hiding at the bottom of this table 9-4 that says we're going to allow shear stresses in the base material of a fillet weld to equal 40% of the yield strength of the base material. That's our design code. So we not only calculate stresses in the weld material through the throat, but we're also going to calculate stresses in the parent material that joins up with the weld material. And we have a separate strength. We can choose our welding wire and be quite strong, but we have a separate strength of the parent material. I believe this is where the lecture stopped on that previous Friday, so that's where I'm going to stop the lecture right now.